Hey everyone, welcome to Spark Talk, brought to you by the Spark branch of Electronics Club at the University of Moratuwa. And today, for our very first episode, we're starting with something literally out of this world, Project Phoenix. I'm sitting down with 𝐻𝐫𝐞𝐜 𝐿𝐿, a final year student at the University of Moratuwa and the chairperson of this very own project. So, thank you for being here. The first question is, what exactly is Project Phoenix?
Yes, Chalisa. So this project is an initiative of University of Moratuwa for space technology exploration, CubeSat development and testing long-distance telecommunication capabilities, and also collecting and analyzing high-altitude sensor data. So this project started as a collaboration between Spark branch of Electronic Club and the SEDS Mora chapter of University of Moratuwa.
As you mentioned about space tech, I think it's a massive domain, especially when you're talking about everything from high altitude sensors all the way to actual satellites. So how do you even begin to tackle a scope like this? What are the phases behind this?
Yes, to handle this scope of the project, we divided into two stages. Stage one is to design a high altitude balloon. Our team is already completed the designing of circuits for this high altitude balloon. We are planning to launch it with the collaboration with Meteorological Department of Sri Lanka. Then the second stage is about cube satellites. Even in that stage, we has two parts. One is to design a ground station. So we are designing a ground station to connect with TinyGS global network for satellite communication. Then after that, we are going to design the cube satellite. This ground station and cube satellite stage, we are collaborating with NUS Star Center, Singapore.
So now that you mentioned about these two stages, I think we'll be missing out if we don't hear more about these two stages. First, let's hear about the stage one high altitude balloon.
These high altitude balloons are going to go in high altitudes. So it will experience a very low temperatures, like even after 10 kilometers it will go for -50 Celsius. So our circuits, already designed circuits, were going to handle these temperatures with proper structures around it, and this balloon will be a helium balloon, so it will go for, as I mentioned, very high heights. And the other challenge is the wind speed, so it will move very fast at high altitudes. Then we are going to recover it through a parachute. Also, it will send the data to our ground station, which we save. Even after recovering, we can get other data from the payload circuits.
A lot of information about the stage one. So now let's talk about the stage two, CubeSat development.
Yes, so cube satellites are very interesting topic these days, because in recent years like 2022, 23, 24, more than 300 cube satellites were annually launched with commercial service providers for these satellites. So these satellites are very small, 10 centimeter sized cubic shapes. So we say it as a 1U cubic satellite. If it's stack 2, then 2U, we mention it as that. We have advisors like 𝐏𝐫𝐶𝐽 𝐿𝐿 from our own department, currently a senior engineer at ST Engineering Singapore for the satellite design. In this stage, as I mentioned previously, now we are designing a ground station called TinyGS. So it's the largest satellite tracking network in the world, and it's open source communities there for it. So currently we are progressing with that step. Then after high altitude balloons launch and everything, we are planning to move for cube satellite development with NUS Star Center.
So you're moving from a high altitude balloon in stage one all the way to a global CubeSat network in stage two. I think that's a huge leap. With a scope that massive, the engineering complexity must be off the charts. So how is your team actually structured to handle all of this hardware and research without stepping on each other's toes?
Yes, so since the scope of these research areas were divided in many sub areas, our talented team configured as 5 subsystems. Power subsystem, which focus on supplying the battery power for the units in the sky. Then communication subsystem, which handles the telecommunication capabilities, uploading, downloading signals for the ground station from the high altitude balloon. Then the altitude determination and control subsystem, which do these controlling parts of the altitude balloon and collecting sensor data. Then structure, payload and thermal subsystem will handle this thermal isolation, structural things of the project, mostly mechanical aspects. Then onboard computing subsystem will do the computing parts of the project for telecommunication. Then the control subsystem, they need computation power provided from this onboard computing subsystem.
So basically 5 different subsystems working on one payload, right? So, but with so many moving parts, how does that actually work? How do you make sure that what is happening in one subsystem is actually syncing with another subsystem?
Actually, we have a very talented team behind each subsystem. So, for example, today we have Mihran from telecommunication subsystem leader, also the control subsystem, altitude determination and control subsystem leader Pravindu will share some experience on their designing process of each subsystem. We can have a talk with them and see how's their subsystems, progress of their subsystems.
Yeah, so as a communication subsystem, our main task is establishing a reliable communication between the balloon and the ground, and also to track the balloon. So basically for this task, we are mainly focusing on the LoRa, because there's it's in the high altitude, so there's no other way, and so we decided the LoRa is the best answer for this problem. So to use the LoRa, we are mainly using e-byte transceivers to establish the two-way communication, because we have to get the data or the sensor data from the balloon to the ground and also send some controlling signals back to the high altitude balloon. So for that we are actually using LoRa, and we also do the tracking of the high altitude balloon. So for that we are using GPS receivers, and also we have also using the radio ondes as a backup mechanism. So that's actually what's been done in the communication subsystem. And what about you, Praveen?
Yes, and as the control subsystem, our tasks mainly revolve around determining and controlling the orientation and altitude of the payload, as well as collecting sensor data from the environment. For the high altitude balloon, our main role is to collect meteorological data from the atmosphere, as well as inertial data, that is, the data that relates to the motion and the movements of the balloon from the payload. We also send the trigger to trigger the release mechanism once the balloon reaches a predetermined height. For the CubeSat satellite, our responsibilities expand significantly, as we have to precisely determine and control the orientation of the CubeSat satellite in order to facilitate the other subsystems processes such as communication, imaging, and energy harvesting.
It's great to hear how all of these different pieces fit together, but talking about the project is one thing and actually seeing it is another. So I heard that your team has prepared a demonstration for us to look at. What can we expect?
Yes, Charlie. So our team is prepared the demonstration for already built circuits of the high altitude balloon stage 1. We can go and have a look on the circuits and how they work.
Now we have Doshi with us right now, and she will walk us through the demonstration. So Doshi, where are you taking us?
Yeah, everything's set at the University tennis court. Let's go there.
Yeah, let's go then.
Now we are at the tennis court to see the live demonstration. Let's see what they're up to.
Yeah, I'm so curious to see how the project has turned out. So can we get a brief explanation about what's going on in here?
Yes, here we have our onboard computing circuit, which is in our high altitude balloon, which transmits the signals. And here we have the ground station set up with the laptop, so it receives the signals. Now we have Lasan, Mindya and Chirat. They're going to demonstrate how we can locate them in our dashboard and other aspects of the interface.
So Chirat, this is a dashboard, right?
Yeah.
So how are the transmitter and the receiver weaved in here?
So here you can see the blue color icon represents the place of the down station, and the red color dot shows us the where the balloon is located. And here you can see the camera feed, live camera feed from the weather balloon. So you can see that, and so here you can see the telemetry data received from the balloon, the altitude, the longitude, the latitude, and also the distance from the weather balloon to the ground station is also shown. So when your weather balloon is not with you, like, you can find what is the location and you can track it, and also other weather information like the temperature, and also the signal strength, and also the signal to noise ratio in the communication between the weather balloon and the ground station is also shown here.
So I see that these 2 points are quite close. So can we take the transmitter somewhere there and see if the distance changes?
Yeah.
Sure. So we can see camera feed also moving with the transmitter, and transmitter's location is also moving. Also, SNR signal ink also changed, right?
Yeah.
What's the reason for that, Chirag?
So probably it's because the distance between the weather balloon and the ground station is now farther, so that should
We can see it moving nicely on the tennis court, right?
Yeah, it's really beautiful.
So speed also, I think, changed, right?
Yeah.
We can see the view camera also from the. Yes. Yeah, now we can see he's moving, and red dot also moved very far from the ground station.
and also the path where the weather balloon moved is also can be seen. So
Red color line is the path it
yeah.
goes and comes. Right? Also distance, where's the distance?
Yeah, the distance is here it's like 45 meters.
Okay.
So and also the latitude is also calculated.
Great, now that we've seen the live demonstration, shall we go to the digital lab to see the technical aspect of this setup? Exactly are we seeing here in terms of hardware?
So right now we are the prototyping condition of the weather balloon, and as of sensors we have used a temperature sensor to monitor real-time temperature of the payload, and we have used two inertial measurement units, IMUs, to calculate acceleration and the orientation of the payload, and we have used sensor fusion to get more accurate data by using two of those data. And for the identification of real-time location in terms of longitudes and latitudes, we have used a GPS sensor, and all these sensors are managed by a central controlling unit, and that is ESP32S3 microcontroller, and we have used a Raspberry Pi board with a high definition camera to capture real-time visual data, and for long-range communication we have used LoRa modules for transmission and receiving of data in real time.
Once the data is collected, how is it transmitted to the ground?
The data is transmitted wirelessly using a long-range communication link based on LoRa technology. This allows us to send real-time telemetry from the payload to the ground station during the flight.
Why is real-time telemetry important to the mission?
Real-time telemetry allows us to monitor the mission as it happens. This includes not only the environmental data but also system-level information such as signal strength, payload status. Reliable communication is critical for both data collection and payload tracking throughout the flight.
So what happens once the data reaches the ground?
On the ground, transmitted data is received by a dedicated LoRa receiver connected to a computer. You can see the incoming data packets arriving real time, which confirms the end-to-end communication from the sensors on the payload all the way to the ground station.
How is the received data visualized?
The received data is processed and visualized using a custom dashboard. It provides a real-time view of key parameters such as temperature, humidity and system health through live plots and numerical display.
Could you show us?
Yeah, so you can see on the web interface, you can see the map, and on the map, your ground station and the current location of the weather balloon is plotted, and also the telemetry data received from the weather balloon can be shown, can be seen here. The altitude, longitude, latitude, speed, and the data from the IMU, inertial measurement unit, and the signal to noise ratio in the communication between the weather balloon and the ground station, and the signal string, and also the camera feed can be seen on the web interface.
So what is the purpose of this dashboard beyond live monitoring?
In addition to the real-time monitoring, the dashboard is designed for post-mission analysis. Once the payload is recovered, we can analyze the full dataset to study trends and evaluate system performance.
That demonstration was incredibly informative. Actually seeing the hardware running really puts all the theory you just talked about into perspective. So a huge thank you to you and your entire team for taking the time to walk us through everything today.
Yeah, thank you very much for inviting us today. Let's meet next time after the high altitude balloon launch of what we built.
For sure, I'll be looking forward to it. And that's a wrap of our very first episode of Spark Talk. A huge thank you to everybody tuning in across all our platforms. And we'll be back next time with yet another great project from our department. So until then, keep building and stay curious. This is Spark Talk.